Okay, so let me start the lecture. So first, yes, there was a lot of questions about this H-bar counting that I mentioned, and I didn't say things quite correctly, so I have to rectify. So let me start with that, like the first 5 minutes before I get to the main topic. So if you normally, yeah, we work in the units of H-bar equals 1, yeah, then we never see H-bar, yeah. But if you rectify it, yeah, the way it enters, for example, the path integrals is like that. And so it enters here as one of it divides the action here. So you can say that the units of action are H-bar. And then let's say that the action, yeah, you have some fields. Can be a scalar, so it's integral for x, and you can have a scalar field d nu phi squared minus m squared and phi squared, and then you have some higher order interaction with k derivatives and n fields. So kinetic terms, yeah, dominate the path integral. So you can assign to each field, you can assign H-bar to the power of 1/2. And then you see that if you have an interaction with n fields, it doesn't matter how many derivatives, so that the action has units of H-bar, you need to assign to this H1 minus n-half. So it means that, for example, if you have cubic interaction, the coupling, so the cubic interaction and the most typical one, like gauge interactions, for example, the coupling then has a unit of H-bar minus 1/2. So this is quite useful, actually, this counting in the SMEF, yeah, because it allows you like immediately say there's one more thing, yeah, and I have to add, yeah, that each loop, as is usual, adds a factor of H-bar. So this comes from the fact, yeah, that the propagator goes like h, and the vertices goes like 1/h, yeah. So number of propagators and number of vertices, yes, is related to the number of loops, yeah. And so now if you so now this is a useful mnemonics, yeah, to understand, yeah, how the Wilson coefficients depend on the couplings in the UV theory. So, for example, if you take 4 fermion couplings, yeah, the Wilson coefficient of this 4 fermion coupling will have, by discounting, so here n equals 4, so it will have a unit of H-bar minus 1. So if it now comes from in the UV theory, you have a coupling that I will denote G star, and it will say it's some kind of a gauge coupling, then so we immediately know that C, so that the H-bars agree on both sides. If C is generated at tree level, we need so this has to have a H-bar minus 1, so it has to have 2 powers of the coupling, and then 1/mass squared, just to account for dimensions. So it's like a very, very useful counting. But now apply this to the dimension 6 operator C F mu nu cube. You know, the one that I was saying, that one of the ones that I was saying that is loop generated. And this in this case, the counting of the Wilson coefficients is This is n equals, so you have 3 fields here. So this has h bar minus 1/2. So now if you want to match it to a UV theory, you would write, you would have to write at tree level, you would have to write that CF is G star over m squared. But this doesn't make sense, yeah, because you cannot have a Wilson coefficient that depends on 1 power of the coupling, yeah, because you integrate out the particle, yeah, this couple, so it has to be emitted and emitted and then absorbed. So there has to be at least 2 powers of G star, yeah. So this cannot be. So the only thing you could have is you could have a G star to the cube at 16 pi squared m squared. And now here you have h bar minus 1/2. Here you have h bar minus 3/2, but then you have to add h for the loop factor, and then it agrees. Yeah. So this shows that this operator can only be generated at loop level. That's a very simple power counting trick that is useful in many applications. If you also apply the same counting to the h to the 6 operator, you'll find that if it's generated at tree level, it has to go like 4th power of the coupling, and because this 6, so this has CH has 1 minus 3 over the high h to the power of minus 2. Yeah? So you need 4 powers of gauge couplings there to account for that. So this is useful. So what I said wrong is that this doesn't explain why this operator, h dagger f, h, for example, h dagger r, b mu nu, why this is generated at loop level, because this has 4 fields. Yeah, it cannot really explain it for a simple reason. Yeah, that I was just showing is that you have a model with an axion coupled to b mu nu, so you can get this operator at tree level. Only that the coupling of the particle is non-renormalizable. But in this argument, there is nothing about renormalizability of the couplings. Yeah, so it's not. This just doesn't enter. So this argument cannot exclude this. So I think you can get this argument. You could understand this argument if you go to the broken phase, yeah, because then it becomes it becomes a cubic operator, yeah, but you would have to go away from the unbroken SMEF, yeah, and make this argument in a different way. Okay, so the same is also for the dipole operator. It's also for fields, yeah. So it's in the SMEF. It doesn't explain it why. So in this case, you have to add additional input, yeah, to this argument. Yeah, it's just not just power counting. Yeah, you have to add something. Okay, so that was the appendix to the lecture, the previous lecture. Let me yeah. No. It can be generated at one loop level if it's even if it's CP violating. Why is that? I mean, it's just a question of how many fields you have. Yeah, how many phases? Yeah, there are. Yeah, but I think that there is no problem generating this at. I think so. I will check it, yeah, but I don't think there is any problem in generating it at one loop level. But yeah, you see this. Yeah, I think there is this. Or how you generate particularly the Weinberg operator. Yeah, I think you would need to have something that that is chiral. Yeah, so in the loop. Yeah, so I mean I mean of course it cannot be just the QCD. Yeah, it has to be something that something I don't know, something like leptoquark. Yeah, that has a color charge but it's a chiral, and then of course you have to worry that the whole theory is anomaly free. Yeah. Yes. Yeah, so it's the same situation like this. It has four fields. Yeah, so this argument has to be amended, yeah, by additional arguments. So it's not just power counting, and that explains. Yeah. So yeah, we get it at one loop. Yeah. Yeah. So I mean, this counting will tell you, yeah, that you can get it at one loop too. Yeah, but it would just not tell you that you cannot get it at tree level. Yeah. Okay, so the topic of this lecture is pole observable. So this relates. This is will be about Z and W bosons decaying on shell. Yeah, so you produce a particle on shell and then it decays. So the point is that we had a lot of information about this decays, which allows us to place very general and quite strong constraints on a large set of Wilson coefficients, and that is what I will be trying to explain in this lecture. So this comes from the fact that in the years long ago, there was a collider. There was a collider that was called LEP. In the first phase, it produced order 10 to 7 Z bosons, 10 million. So that allows, because most of these bosons could have been detected, then this allows you to have a precision of your observables that is per mil. So more or less like it goes more or less like a square root. Then there was a second phase, of this LEP. It was called LEP 2, and where so this was running on the E plus E minus had a square root of mass energy that was tuned to the Z boson mass. Then the square root of mass energy was increased, and then this collider could also produce the W plus W minus pairs. But because when you're off pole, the cross section is smaller, then there was something like order 10 to 5 bosons. So the precision that was obtained for W bosons was a bit inferior. It was closer to the percent than the per mil. And then W and Z bosons are also produced at Tevatron and LHC. For example, at the LHC, at the cross section, for the production of the W boson, is 20 nanobarns. So it's huge. And given that we have with 50 inverse femtobarn, you can count that this is the luminosity that more or less was collected. So far, it gives you 10 to the 10 W bosons. So you have a huge sample, also of W bosons and similarly Z bosons at the LHC. Unfortunately, the LHC is much dirtier environment. So you can only see really leptonic decays of both the W and Z, if you want to do any precision studies. So and you have systematic errors that allow you for W bosons allow you to barely surpass the lab accuracy, and for Z bosons, yeah, the accuracy hasn't yet reached the one that was obtained at lab. So that's the experimental background. So let's be more precise. What has been measured so far? So first, one thing that was measured is the Z boson mass, and the Z boson mass is measured, yeah, with a relative precision, yeah, of 2 times 10 to minus 5. So it was a fantastic precision, yeah, because lab was able to like tune energy of colliding E plus E minus, and then see exactly the line shape of the resonance. Yeah, from that you could measure Z boson mass with a fantastic precision. Yeah, so that corresponds to more or less a 2 MeV error. Yeah, that boson mass is 91 GeV more or less. Yeah, and then you have a MeV. For the W boson mass, so actually that's where so that's one point where Tevatron and LHC surpassed, yeah, the precision, yeah, of lab, and here you have more or less 1.5 times 10 to minus 4 precision. Yeah, so less, 10 factor of 10 worse than for MZ, but still quite impressive. Yeah, so this corresponds to something like 13 MeV error. Unfortunately, yeah, there is a catch here, yeah, for the W boson mass. Yeah, that W boson mass seems to depend on where you are. Yeah, so it's quite different at the LHC and at the Tevatron. Yeah? So this okay. I had it later. This number I forgot. So more precisely, yeah, when you look at the particle data group, yeah, there is this measurement. The latest W boson mass gives is this. So this notation means that it's 80 GeV, 369 GeV plus minus 13 GeV. Yeah, so I don't know if everybody's seen this kind of notation. So instead of writing plus minus, yeah, you just write the error corresponding to usually to the last significant digits in the number. But there is a measurement that is from Tevatron's CDF that came several years ago, that is has a smaller error than this, and it's not included in this combination because it's more than 5 sigma away. So nobody knows what happened. This is like a very 6 sigma, yeah. So the MW CDF is 80.4335994. You see that there is one more significant digit here for the error. So the error is 9 MeV, but this is very far away from this result. Yeah, so for the field of precision physics, it would be much better, yeah, if CDF never made this measurement, because this mess is not likely to be solved anytime soon. Yeah, we'll never know what to do with this measurement. But this is based, yeah, on lab measurement, Atlas, independent Atlas, and CMS, and even also LHCb measurements. Yeah, they all seem to converge, yeah, to a different value. So also earlier CDF measurement and D0 measurement at the Tevatron also agree with this value. There's only just one outlier. And so I think the best strategy, yeah, that is also seemed to be taken by a particle data group here, yeah, is to ignore this, yeah, that this never happened, yeah, and forget about it. and we just work with this. Okay, and that's what we're gonna do here. So this is so these are the masses, and except for the masses, then we have a measurement, of the different observables with a more or less per mil precision. So this is the width, the total width of the Z boson. The hadronic cross section, which is proportional to the width, partial width into electrons, times partial width into quarks, divided by the total width. Then there is measurements of something that is called leptonic ratios, which for some unknown hadrons, Z into hadrons, it's defined opposite, and it has the leptons in the denominator instead of numerator, but that's how it's defined. And this is measured for L equals E, mu, and tau separately. Then we have a heavy flavor. This is heavy flavor fraction, and this is hadronic, and for Q equals both C and B. So that's also quite impressive, that lab identification of C was almost as good as the identification of B. So this is like, this could be measured, with the 10 to minus 3 precision. Then there is also measurements of left-right asymmetry. So left on left minus gamma, then left on right divided by gamma Z leptons. And then there is we have also similar measurements, for the there is forward-backward asymmetry measurement, which is just given by 3 for AL squared, and then there is a forward-backward asymmetry for heavy quarks again. So this is the set of observables, that is measured very precisely, and we will try to discuss, how this is how this is constrained by the how does this constrain Wilson coefficients. For the W boson, we also have a measurement of the, maybe just here, the total width and branching ratios into leptons. But here the precision is something more like 10 to minus 2. So for here 10 to minus 3 precision, and for the W bosons, a bit weaker. There's some more observables, usually with less precision, that this will not be discussed. So now, in the standard model, at tree level, all these observables, are given in terms of three parameters: GL, GY, and V. This is the or more precisely, or equivalently. Okay. So this is SU2 electroweak coupling. This is the U1 hypercharge coupling, and this is the Higgs depth. So at tree level, all these observables, are functioning of the three parameters. At loop level, you have also significant dependence on MT and MH, but I will not be concerned with it. So in all this precision business, yeah, I'm a BSM user. I'm interested in BSM corrections mostly. So I let other people, more skillful people, to calculate the standard model corrections. And I'll be interested, yeah, in the BSM corrections, yeah, because for BSM corrections, you don't need to calculate higher order corrections. You don't need to be very precise because you're calculating an unknown effect that is already small. So higher order corrections, yeah, are even smaller. So that's the. So now, how do we know that this will be important, yeah, for the story? Yeah, how do we know what are the values of GL, GY, and V? So these are taken customarily from input observables. You select certain observables as your input to determine those. And it's like for organizing calculations, it doesn't really matter if, in the end, but for organizing calculations, it's best to take the most precise observables you have to determine those, and then use the rest of the observables to determine other parameters. Yeah, so in the standard model, you can use this then to determine MT and MH. Yeah, and beyond the standard model, yeah, we'll be treating this MT and MH as fixed because they are measured otherwise, and we will be constraining, yeah, Wilson coefficients. So the input parameters that are usually chosen, yeah, is alpha, GL, GY, square root of, oh, sorry, this is GL squared, GY squared, GL squared plus GY squared, 4 pi. And G Fermi, which is calculated which is extracted from mu on decay width. So mu on decay width, you can write it as G Fermi squared m mu to the 592 cube. Yeah, and then 1 plus corrections. So out of this is defined from G mu already unfolding the various QED corrections, yeah, that are entering here, and MZ. So we have to take one of the observables of this precious set to determine our standard model parameters. So we have 3 observables. By the way, so yeah, I have to say how this is how GF is related to the electroweak parameter. So GF can be defined as a coefficient of an effective operator. It's defined like this. Like when you go to the or maybe write it left. So yeah, minus 2 square root of 2 GF epsilon bar sigma bar mu, and then mu bar mu bar sigma bar mu. So it's GF is defined as a Wilson coefficient of a 4 fermion operator that gives you the muon decay in the effective theory below the Z and W mass scale. So you can calculate this operator. So in the so maybe just add that this is given by GL squared plus GY squared over 2 times V. And so so this allows me to, it will allow me to calculate how GF is related to V. If you start with in the standard model, you will have a interaction, yeah, of W boson. Minus bar sigma bar mu. plus mu bar, sigma bar, mu. Sorry, maybe there is a clash between mu particle and the mu index. So let me write it like that. And if you, this contains also the W mass, plus W minus, and then it also contains H bar, the Hermitian conjugate, yeah, of this operator. So then when you integrate out the W boson, you will find that W mu plus is equal to minus GL over square root of 2 MW squared E sigma bar rho mu E plus mu bar sigma bar rho mu W rho mu. And then when you plug this back into the Lagrangian, yeah, you will get that the lambda, so the Lagrangian effective. So from this, you will get plus GL squared over 2 MW squared. And then E bar sigma bar rho mu E plus mu bar sigma bar rho mu, and then the other way. Mu E sigma bar rho E plus mu bar sigma bar rho mu. And then when you plug it here and here, yeah, you will get the same, but with an opposite sign. So you will get minus. There's no minus here. And now we use also that this is equal to GL squared over 2 GL squared V squared over 4. So it's equal to 2 over V squared. So if you compare these two formulas, you find that GF, I write it here together with everybody, GF is equal to 1 over square root of 2 V squared. Yeah, so this is the relation. Yeah, so you can use, this is actually a definition of what the Higgs bath is, yeah, in as a parameter. It's tied to the value of GF measured at low energy. So you see that we have these three input parameters, yeah, that are measured very precisely, and from that we can measure we can know these parameters GL, GY, and GV in the standard model, and this allows us to constrain other things. And what I'll be interested in is constraining the dimension 6 operators beyond the standard. So let me give you one example of how we can constrain. Yeah? No, they are definitions. So in this case, they are, so first, this is not they're definitions of what we mean by GL, GY. If there is a loop correction to this, or we'll see also that there will be corrections from Smith, we have to change the meaning, yeah, of redefine GL, GY, so that this relation is true. Yeah? This is a definition, yeah, of the couplings, and then if observable obtains a correction, it has to be absorbed into the definition of the couplings. That's the for all of this, yeah. Alpha depends on what? Scale, yes. So this is usually defined alpha at 0. Yeah, that's the quantity that is measured very, very, very precisely. Then what you need to do in practice, you have to run it to MZ, and then the alpha has a much bigger error, yeah, because the running is there are non-perturbative corrections. So the running, yeah, is called alpha 5 hadronic, something like that, yeah, and then it has to be, it makes the error larger. Sometimes this alpha 5 hadronic is also determined from the fit, yeah. Yeah, so sometimes it's used, you can, alpha 5 hadronic is used as an input also in the fit. So it's like a nuisance parameter, yeah, that you don't know and how to. But yeah, as I said, we will be, my perspective, yeah, is BSM, yeah. So it's, of course, these are important things, yeah, but these are left, yeah, for people who do the standard model. And I'm mostly interested, yeah, how this picture changes when you have higher dimension operators.
The order of one loop.
Yeah, yeah.
So you actually have to have a comparable SM at one loop done totally.
You should at the current, I think, precision, you should have, I mean, yeah. So SM is done at one loop, yeah. Right. Yeah, if one, so and this is I think enough for the current precision. Also, some two loops are known. It is known, yeah, that if you for a future collider, we will have to go to 2 and sometimes even 3 loops, yeah, to have this right. Yeah. For the moment, the calculations, yeah, in most of the, in almost every case, yeah, the theoretical error is much smaller, yeah, than the experimental error. I think the difference is the only exception is MW, where theoretical error is still smaller than experimental error, but not much smaller. It's factor of 2 smaller only. In most cases, it's factor of 10 smaller. So
I think is that if you do it systematically, right, the top,
yeah,
observable non-trivially, like like that. So that's not just bare bone Fermi theory, right? So how do you think of that?
No.
How do you insert those operators?
No. So you would have to. You would have to integrate it out, yeah, and it would go again into the definition of V, yeah, like all the dependence, yeah, on this is I think this is what you're talking about is a small effect, yeah, that is not very important, but
MT square by MB square.
No, but if that's
log of MT square by MB
for this for GF, yeah.
Some of them, because isospin breaking in some speed.
Okay, yeah. So I don't know this precise this detail. We can try to work it out maybe later. So let me give you one example. Maybe I make this will be needed. So here, and then one example of an operator. Lambda d equals 6. We have this kind of operator. E I H dagger d mu H and EC sigma mu e bar C, and then CH. So what does this operator will do to us? You can show, yeah, that this is that H dagger d mu H, after you put the Higgs wave, will give you minus E V squared over 4 square root of GL squared plus GY squared Z mu. So now the L d equals 6 will contain, so this arrow means it's minus the Hermitian conjugate, so it will be twice this. I's will cancel, and then you have a CH V squared over 2 square root of GL squared GY squared Z mu. this, you see. Yeah, so this is a coupling of Z mu to right-handed electrons. Now, yeah, so this is the whole SMEFT will contain also the standard model couplings of Z to right-handed electrons. Yeah, so this will be Z mu. So Z couples via T3 minus sine theta squared Q. T3 is 0 for right-handed electrons, so there is only this piece, and Q is -1. So there is gy squared over gl squared plus gy squared plus delta g ZER, where delta g, where delta, this is equal to minus CHE d squared over 2. Yeah. So what happens is that this operator gives you a correction to the Z coupling to right-handed electrons. Right, that's it. Right. So how do you how you can constrain it? Yeah. So for example, you can use this observable. That will be like just as a simplest calculation to do on the blackboard. This AE is equal to gamma Z to EL minus gamma Z to ER divided by the same thing with a plus. So this we can just write as GZEL squared minus GZER squared over the same thing with a plus. So the coupling of Z to left-handed electrons, yeah, will be given by similar formula, but it will have a 1/2, and assuming that this is the only operator that's an assumption for now, then we'll have a minus tau plus S theta squared, and then minus S theta squared plus delta ZR squared, and divided by the same thing, plus. So now we are you can write it as, when you just, sorry, forgot the squared here. You can write it, yeah, as 1/4 minus S theta squared minus 2S theta squared delta G ZR divided by 1/4 minus S theta squared plus 2S theta to the 4th. Sorry, I didn't define S theta, but S theta squared is GY squared, L squared, GY squared. And plus 2 S theta squared delta G to that Y R. So now look, I already did one thing here. I neglected quadratic terms in this delta G. So the reason is that I'm looking at the first order corrections, the dimension 6 operators. So I'm working up to order lambda squared in the observables, and ignoring everything that is over lambda to the 4th, because that is the same as dimension 8 operators that I haven't taken into account. So this is and now we also have to write it, take it out of the denominator to have it. So we'll have 1/4 minus S theta squared 1/4 minus s theta squared plus 2 s theta to the fourth and minus 2 s theta squared delta g z e r times factor. Squared divided by 1/4 minus s theta squared plus 2 s theta to the fourth squared. So yeah, there is this factor, yeah, that comes out. It's correct. Because I had to expand the denominator. So this, you can call it a y SM. So this is the standard model prediction, and this is the correction. And here we can just put number. Here we don't have to be very careful what the number we put, because yeah, if we put what s theta, whatever s theta we put, yeah, whether this is yeah, but you just take you can, for example, define s theta like that here, and here you have to be very careful what you put, yeah, because you cannot, if you just put this number, this is a tree level only expression, so it will be off from the experiment by more than 3 sigma for sure. You have to take the number with all the standard model corrections, yeah. But somebody else calculated it for me. It is known what it is, or there are programs where you can calculate it, yeah. And so I just take it, and then I evaluated this, and I get something like minus 4.2 delta GZ ER. Yeah. So now I have an so yes, this calculation, yeah, is just to show you, yeah, what kind of strategy is used, yeah, to do this this fits to new physics. And so I take AYSM experiment is 0.151621. So by the way, I completely forgot when I was saying about the experiment that there was also one more experiment, a collider experiment that was doing the measuring this precision electric observables. That was the linear collider in SLAC. And actually this observable, it comes from that collider, because they were the ones that had polarized beams. LEP also measured some polarization asymmetries, yeah, but they were using some tricks, yeah, to do it, yeah, and they never had polarized beams there. And so, and their precision, yeah, is much lower. And yeah, this AASM is equal to 0.1472 with a negligible error. Yeah, so the error is much smaller, yeah, than the. And this number includes all the corrections. Yeah, so you get that you can extract what is this delta GZ, or if you write it in terms of the Wilson coefficient of the operator, where was it? This is, you can write it. Yeah, this is 2 plus 2.1 CHE times V squared. And then you extract, yeah, from these numbers, yeah, that CHE times V squared is equal to 2.2, 1.0 times 10 to. Just keep it on the side of the board. 2.2, 1.0. So this is the constraint you get from this particular observable, and this is actually not the most constraining observable. So if you assume that this is the only operator, and you make global fit to all the observables, yeah, that I listed there, you're getting a stronger number. You're getting something like 2.2, 3.2 times 10 to minus 4. So you can get an error by a factor of 3. And actually, the most constraining observable for that would be a hadronic cross-section measured at LEP, which is measured very precisely, and it has. And also, you see that here you're getting some 2 sigma tension, yeah, but when you do the global fit, this completely disappears. And so that's the advantage, yeah, of doing the global fit. So in the remaining 10 minutes, let me give you one very important example of a different operator, and which will enter in a different, will affect the observables in a slightly different way. So let's take the observable, this operator, CHD, and H dagger d mu H squared. So now if you write down, yeah, the covariant derivative here, yeah, you find that d mu H will be something minus EV over 2 square root of 2, and then something, whatever, it doesn't matter because it will be projected out by the VEF of the Higgs, and here you have square root of GL squared plus GY squared Z. So now when you multiply it by the Higgs, write it, but it will contain, and then when you multiply it by the Higgs VEF here, it will be multiplied by another V over 2. You're getting that H dagger d mu H is minus I V squared over 4 square root of GL squared plus GY squared Z mu. So lambda d equals 6 will contain CHD V to the 4th GL squared plus GY squared over 16 Z mu, Z mu. Okay, so what happened is that in the presence of this operator, mz squared is equal to GL squared plus GY squared V squared over 4, 1 plus V squared over 2 CHD. So this is, of course, this is a tragedy, yeah, because we were using mz as to set our couplings. So one thing that you're not allowed to do, of course, is use now measurement of mz that is, for example, here. I didn't write the exact number, yeah, but yeah, and then try to constrain CHD from that measurement, yeah, because you cannot do that, because that measurement is used to determine the electroweak couplings. And so what you have to do, I mean, you could do two things, yeah? You could do a global fit, yeah, where both the standard model couplings and this operator are the parameters you fit, and then you fit everything all together. Input observables, yeah, and all the other observables. This is not the most efficient way, and also it's very unstable when you do this fit, because you see that this I haven't actually, you don't see it here because I haven't written it, but this observables, for example, GF, has a precision, yeah, of something like 10 to minus 7. It's much actually. Did I write? I think it's 7. Yeah, but okay. It has a much better precision, yeah, than the other observables. Also, MZ has much factor of 2 orders of magnitude better precision. So when you do the fit, when some directions are very constrained, yeah, and some are less constrained, this is very unstable. So the better way is to redefine your couplings. You can say now that GL, GY is you define a new couplings, twiddle couplings, such that in terms of the twiddle couplings, mz squared is exactly GL squared plus GY squared V squared over 4. And at the same time, you want to define it such that you also don't screw up the alpha, so that alpha is still GL squared, GY squared. So it's exactly as in the standard model for pi. Okay. If you do that, yeah, so the solution to this is the following. You have to choose delta GL equal to be minus GL squared over 4 GL squared minus GY squared, V squared CHD, and delta GY is equal to minus GY squared over 4 GL squared minus GY squared, V squared CHD. So you can see that, yeah, if you add this, and yeah, no, not the minus, it has to be plus. If you add this two things here, right? So here we are at the dimension 6 levels. The difference between GL and twiddle GL is ordered at dimension 6, yeah? So it doesn't matter whether I write here GL or twiddle GL, it's the same thing. So if you do that, yeah, you can, this is a very simple calculation to see that this will cancel this, so that then indeed we'll get this formula for mz squared. And this is a little bit more, but yeah, you will put it on a Mathematica or whatever, and you find that this is also satisfied. Yeah, this is a little bit more complicated. Yeah, but this you can do. Yeah. So now you see that the effect of CHD vanished, but it didn't vanish completely. It will show up elsewhere. For example, you see that MW was not affected. So we are assuming here that MW is so like this is this is the only operator, yeah, for the moment. So MW was given by GL V over 2. So you see that what we actually determine now from the input is not GL, but GL twiddle. So we have to express it by something we know, which is GL twiddle, V over 2. And GL twiddle is 1 minus GL squared for GL squared, GY minus squared, D HD D squared. So we got a correction to the W mass. And if we do the same way, we'll get the corrections to all observables that depend on GL and GY. And now we can measure, from these corrections, yeah, we can constrain this. Yeah, so actually MW is the most constraining observable. So if you do this, no, but I think I define it like that, yeah, that GL is GL twiddle 1 plus delta GL, and delta GL was minus. So I think it's like that. I'm not sure you understand.
V can be correct.
Yeah, V can be, but not by this operator, yeah? So this operator doesn't correct V because it doesn't affect anything. It only affects MZ, so it only changes GL and GY, this particular operator. And then you can constrain, you can take the measurement. I think I already wrote the MW, yeah? So yeah, you solve it, yeah, and then you find that V squared CHD is equal to 3.5 times 10 to minus 4. You're getting a constraint of the order, yeah, of sub per mil precision. But you're not getting the 10 to minus 5 constraints from MZ, but you're getting a 10 to minus 4 constraint from MW. And then if you, yeah, this is consistent with the standard model prediction, yeah, and if you actually make a global fit, yeah, this will be very, very similar number, yeah, because MW is the most precise measurement. So this is, yeah, this is how you have to do it. There are other operators. Let me just finish with this. That there are other operators, yeah, that affect input observables. One other operator is this. Well, I should have this one. mistake, but yeah, there is this operator lambda d equals 6 equals CHWB, H dagger sigma K H, W mu nu K B mu nu. And this, when you put a VEF, you get a mixing between Z and gamma, and also corrections to Z, Z normalization and gamma normalization. When you undo it, it will show up, yeah, in all over the place, yeah. In part, it will show up as a corrections to alpha. It will show up as a correction to MZ. It will show up as also corrections to the Z couplings to lepton, and then you have to undo this new effects in MZ in alpha, and then you to correctly calculate the effect of this operator. Another operator is this CLL L1 sigma bar mu L2 sigma bar mu L1. So this is an operator, yeah, that contributes to the muon decay and will shift G Fermi. This one will shift G Fermi, and then you have to undo its effect by shifting V, yeah, by something proportional to CLL. There is also, one should also say that there is also the operators like that, but with left-handed, sorry, okay, maybe I'll write it from the beginning. There is also this operator, CHL3, H dagger, sigma, K, mu H, and then you have L sigma mu sigma K L, because this operator, because of the presence of the sigma matrices here, contributes to the W coupling to electrons and muons, whatever, depending on which generation you take. And then remember when we did this calculation here, that's why actually I was doing it. When you integrate out the W to get formula for the G Fermi, this operator will show up again in the formula for G Fermi, and you have to take it. So this is like the very important point that appears that you to do the this constraints, yeah, properly, you have to take into account, yeah, the contributions, yeah, of higher dimensional operators to your input observables, yeah, otherwise your results, yeah, will not be correct. Okay, so I think it's a good moment for a break. After the break, I will say just a few more words about this electronic precision observables, just about the results, yeah, and then I'll move to topic, yeah, of constraints, yeah, from low energy observables, yeah, on high scales.